Okay, we stopped the last video halfway through page 14 of your lecture notes of lesson 6 because we don't need to make an enormously long video, do we? So we're going to finish out lesson 6 and go right into lesson 7. They are speaking the same thing. We're looking now that we have gotten the vocabulary of molecularity, elementary steps, mechanism, rate determining step, how it applies to the reaction, how to write a rate law. And now we're going to look at example in the middle of page 14 in the box. They've given you a reaction and they've given you the rate law that matches the reaction. And they're asking you now to look at proposed mechanisms and say which of these is the best or can be an acceptable mechanism for this reaction. So let's look at each mechanism separately, all right? Okay, the first mechanism is one step, all right? It does reflect the rate law. It has one step, so it's the rate determining step. The rate determining step however, does not match the balanced chemical equation, does it? All right? So we said if a mechanism is one step, then it has to reflect the balanced chemical equation because your mechanism must add up to the balanced chemical equation. All right, if the mechanism were one step, then it would be rate equals K times NO2 squared times, oh wait a minute, it does, no. And notice our rate law does not reflect that, all right? So this is not an acceptable mechanism because even though it adds up to the balanced chemical equation, it does not reflect the rate law, right? One-step mechanisms must be written from the balanced chemical equation because they're saying the balanced chemical equation is how they collide, how they do it. All right, so now let's look at B. So we've ruled out choice A. Choice A is not an acceptable mechanism, okay? Choice B is one of those where it's two-step and slow step is the second step. So first of all, if we add this up, we do get the balanced chemical equation. All right, so that's acceptable in our elementary steps leading up to a balanced chemical equation. All right, we do have one rate determining step. The rate determining step, however, does not reflect the rate law. Now, does that end it? No, we have to do a little bit more work on this, okay, because the rate determining step includes an intermediate species, doesn't it? It includes that F, monatomic F, all right? So what we have to do is our substitution, all right? So the first thing that we would do is write an equilibrium expression. That's our equilibrium expression for our first elementary step, which is the fast step. All right, now we're going to rearrange this to solve for the intermediate species. And in doing that, then, in doing that, this here is what we would have to substitute for F in the second step. And we can see right away that this does not show up in our rate law, all right? So we can rule out mechanism B, first of all, because it had an intermediate species in its rate determining step. Remember, the rate determining step will reflect the rate law. All right? This is not in the rate law. So even after we've fixed it and got the intermediate species out of the rate determining step, a rate determining step still does not reflect the the rate law. So B is not acceptable. So let's move on to C. Okay, C, if we add those two together, we get the balanced chemical equation. All right? It has one rate determining step. We're good there. The rate determining step matches the rate law. So let's look. The rate determining step is NO2 plus F2. So the rate law is NO2 times F2. Viola, we got it. All right, so yes, C would be an acceptable mechanism because it follows our rules. Now, on the exam, do you say because it follows the rules? No, that would be too vague, all right? So they'll ask you to say why the mechanism is acceptable, all right? And you would say that. It has one rate determining step, and the rate determining step matches the rate law, all right? You don't have to get into a multi-paragraph oratory on this, all right? Just get to the point. Okay, let's move to the bottom of the page. Ozone decomposes into oxygen gas by that following balanced chemical equation. Then they give you the rate law. The rate law for this is really amazing. All right? Does the decomposition of ozone happen in one step? No. All right? Fortunately, they don't ask you to analyze this mechanism, okay? They're going to keep it fairly simple. This actually would be a mechanism that probably had the slow step down about the third step, and you'd have to do multiple substitutions, and it's just, woo! Like I said, one of those things you think, oh yeah, I really get this, and you don't get it at all. But anyways, all right, if this were a one-step mechanism, the rate law would reflect the balanced chemical equation, correct? So if this were a one-step mechanism, this would be the rate law. All right? That would be the rate law if the decomposition of ozone occurred in one step. Because it's not, this is not a one-step reaction. All right? They didn't ask if that was an acceptable mechanism. It says, did it happen in one step? All right? So they want you to understand if a mechanism happens in one step, it will reflect the balanced chemical equation. But remember the cardinal rule. Our rate laws are not gotten, which is wrong to say, from the balanced chemical equation. They are experimentally determined. All right? If in experimentally determining, we determine there's one step, then it will. But it's not the, it's the dog wagging the tail, not the tail wagging the dog, so to speak. All right, so that is the end of lesson 6. Let's move on to lesson 7, which is more of the same. We're analyzing these mechanisms. All right. We have two mechanisms are suggested for the reaction between NO2 and CO. All right? They have not told us the products on here, have they? But we're sharp. The first mechanism is a one-step mechanism. So what does it have to reflect? The balanced chemical equation, correct? So we can still get it. Just make sure you understand where we're getting this from. So apparently this is the reaction. NO2 plus CO goes to NO plus CO2. All right? There's our reaction. reaction, and they give us a rate law. The rate law for this is rate equals K times NO2 squared. This is the rate law, and this is the equation. All right? Now, is the first mechanism feasible? No. Why? Because the first mechanism is obviously a one-step. Now, they didn't write out here step 1, did they? How did we know it was a one-step mechanism? Because there's nothing else under it, all right? Make sure that you don't get the blinders on and say, oh my word, they didn't start out by saying step 1, all right? Now, notice on most of your free response, they have all the steps. But if there's just one, do they really need to say it? How do we know there's just one? Because they only have one step there, all right? And that one step does not reflect this rate law. So that disqualifies that mechanism, all right? It doesn't reflect that it has one step, it is obviously the rate determining step, and it doesn't match the rate law. So done. All right, now let's look at the second mechanism. Does it qualify? Well, if we add them up, we get the balanced chemical equation. All right? It has 2 steps. One of those must be the rate determining step. All right? Did they tell you which one is the rate determining step? No. Do they have to tell you? No, because you should be able to figure it out. All right? Because what do we know about rate determining steps? Rate determining steps must match the rate law. So which of those steps reflect the rate law? The first step, all right? So is this an acceptable mechanism? Yeah, it has one rate determining step, right? The rate determining step that we have also identified as step 1, all right, which is the next question. Which step is the slow step in the mechanism? All right, and we have then the rate law from that slow step. So in this particular example, we have determined a correct mechanism by being given an equation and a rate law. All right? And did they give us the equation? Not really. Could we get it? Sure, because if it's one step, it has to reflect it, right? So see where you can get your sources. I don't think they'd ever do that to you on the exam. They're going to give you the whole equation. But I want you to be a little bit sophisticated, okay? How to not pass out, freak out, run out of the room with your arms flailing because you don't think it's complete or they missed something. They did not miss something. It is not incomplete, all right? You can do it. Let's move on to the next one. A rate law for the following reaction. A plus 2B goes to P, all right? They've determined the rate law, so they've got a rate law associated with it. Rate equals K, right? Here's our equation, and here's our rate law. Now, they've given us 3 possible mechanisms, and they're saying which is the most reasonable, and explain. Okay, number 1 is a one-step mechanism. All right? If it's a one-step mechanism, the rate law must reflect the balanced chemical equation. So A is not acceptable. If it were A, the rate law would look like this. And it doesn't. So it's not acceptable. All right? B. B is one of those where we have the fast step above the slow step. So first of all, we have 2 steps. Do the steps add up to the balanced chemical equation? Yes, A plus 2B equals P. The C cancels out. All right, we can't have an intermediate species in our rate law, in our rate determining step, which they've identified as the second step. So right now, it's not acceptable. Having said that, let's see if we can substitute that C by writing an equilibrium expression. And solving for the intermediate species. Once we've solved for the intermediate species, we can plug this into the slow step. So now let's look at the slow step. And remember, this really cancels out because a constant times a constant is another constant. So we can say A, B plus B equals P. All right. Now let's write a rate law of this. Well, a rate equals K, the rate constant, times the concentration of A, times the concentration of B squared. Now, technically, that was kind of a shortcut, but if we plug this back into the equation, it would look like this, wouldn't it? If you want to be real more technical about it. Because this looks like this in the rate equation, right? You multiply what you've added. So if we plug this back into the equation, it actually looks like that. I didn't write it that way eventually because, initially, because I knew what I was going to do it. But when you write it like this, you have K. Now notice this is termolecular, all right? But it is termolecular kind of in an indirect way, isn't it? Okay, so this is where we say if termolecular is one step, doesn't happen very often. Where termolecular happens is when that slow step is down further in the mechanism and we've done substitution. All right, and this is an acceptable mechanism. All right, let's look at C. Remember, this is our equation, and this is the rate law, and they're saying, do these mechanisms, are they reasonable? All right, and C, we add them up, and we get the balanced chemical equation. We have one slow step. The problem with this one is that our slow step, which is what the step, the rate law, is taken from, all right, would be this. I'm sorry, in B it would not be acceptable because it doesn't reflect that rate law. I'm very sorry. All right, in B we got a rate law that looked like this, didn't we? All right, so that one is not acceptable either because after we substituted, we don't get the rate law. Mechanism 3, however, is it. Yay, we got it, because we have one slow step, there's no intermediate species in that slow step, and the slow step reflects the rate law. All right, so they've given you 3 mechanisms. You must work through them to see if they are acceptable and to be able to quickly just bullet point why they're acceptable. All right, once again, not a 3-paragraph oratory on the acceptability or unacceptability of a mechanism. All right, let's look at one more example. For this reaction, one proposed mechanism for this reaction is that 2-step. Determine the rate law if this mechanism is it. All right? Okay, so the first one is fast. The second one then has that intermediate species in that we have to get rid of. right? Because if we add these two together, we do get the balanced chemical equation, so that part's good. We can't compare it to a rate law because they didn't give us a rate law to compare it to. So now we're just coming up with a suggested rate law based on this mechanism. So let's see how that works. Okay, that fast step we're going to write in terms of an equilibrium expression. Right? We're going to rewrite this in terms of the intermediate species, correct? Then we're going to substitute these values for that in our rate determining step, okay? So and we can get rid of that k because k times k is another constant, so it's irrelevant, right? All right, so after we substitute these values in for our intermediate species, we get this. And so the rate law from this would be rate equals the constant times NO squared times VR. All right. So according to this mechanism, that would be the rate law we come up with. All right? Now they say, here's another proposed mechanism. So let's look at this one. So I look at this one and I say, if I add them up, do I get a balanced chemical equation? Yeah. All right. Does it have one slow step? Yeah. All right. Oops, this one also has an intermediate species in the mechanism, in the rate determining step. So right now, as it's written, this is not acceptable because we can't have an intermediate species in our rate law, all right? So what we have to do is we have to substitute out again for that N2O2. So let's just put this one over here. If we write the K for this particular one, we get N2O2 over NO squared, right? NO times NO is NO squared. All right, so now if we substitute the intermediate species in terms of the rest of this, well, first we rewrite the equilibrium expression in terms of the intermediate species. And then we're going to take this and substitute it into that rate determining step, all right? So we're going to put NO plus VR2 goes to NO VR. And so we get the rate law from this is always rate equals the constant, rate equals the constant times NO squared times VR2. The rate law is from the rate determining step. The rate determining step does not include an intermediate species. We're good. All right. Well, which is correct? Both. Is it possible to have more than one acceptable mechanism? You bet it is. All right. Remember what I said earlier about the silver and gold, okay? Because we really have a hard time with intermediate species identifying them and saying if it is correct, we are just guessing what the intermediate species is. Who's to say that the intermediate species is NOBR2 or if it's N2O2? We can't prove it, we can't disprove it. The only thing about a mechanism is it acceptable? If it meets our criteria, then it's acceptable. And both of these have met the criteria. So both of these are acceptable. All right. One more. Well, not one more. This is a good one because we've talked about intermediate species, and now we're going to look at a reaction, and you're actually going to do this reaction in lab. The decomposition of hydrogen peroxide is catalyzed by an iodide ion. The catalyzed reaction is thought to proceed by this two-step mechanism. Is this a legitimate mechanism? Well, let's see if it follows the rules. Do the two steps. Now this is where your Friday reaction, I hope we all know that the decomposition of hydrogen peroxide goes to water and oxygen gas. All right? It doesn't go to H2O2. That is what water decomposes into. Hydrogen peroxide decomposes into water and oxygen. All right? So we first write the reaction, and we can because we've been doing these all year, correct? All right. So, do the steps add up to the balanced chemical equation? Sure. Is there one rate determining step? Yes. Does the rate determining step include an intermediate species? No. What is the difference between a catalyst and an intermediate species? All right, well, we'll get into that in the next lesson, but just quick, a catalyst first reacts and then pops out at the end, because remember the definition of a catalyst. All right? It speeds up a reaction without being involved in the reaction. Okay? So we put it in as a reactant and it's spit out at the end. And so we just reuse it and reuse it and reuse it. It never goes away. An intermediate species does not show up as a reactant. It is first formed. It first shows up as a product. It's formed and consumed. Right? A catalyst. Yeah.
Do you care if I take my SATs test during third period?
No. On video, okay? Feel free to come in. It's kind of hard to be lecturing to no room, okay? Anyways, okay, so does it follow the rules? Okay, remember that it's okay to have a catalyst in a rate law. Look back at lesson 6 when we first introduced this. We said you could not have an intermediate species, you could have a catalyst. So, the equation for this we've written. Have we analyzed the mechanism to say, is it acceptable? Sure, it's acceptable. So based on this, the rate law, rate equals the rate constant, always start out with that, times the concentration H2O2 times the concentration of the iodide ion. All right, perfectly acceptable. This is the rate law from that proposed mechanism for this reaction that is catalyzed by the iodide ion. All right? Okay, now how about they ask you to write a mechanism? Now what's nice, if they ask you to write a mechanism, it's probably going to be one step because they're not going to expect you. But I'll tell you what, you know, if they want something two-step, then just make something up as an intermediate species. All right, just put X. Have X formed, X removed, and, you know, have the first step be what reflects the rate law, and then you're good, all right? But let's look at this so I can show you. Okay, they give you this reaction that we saw earlier, being the isomer, and they tell you that the rate law is this. Well, what is the mechanism? Obviously, this is a one-step mechanism because the rate law matches the balanced chemical equation. If it matches the balanced chemical equation, it is one step. So this is what I would do. I would say step 1. said, this is a one-step mechanism, and this is the slow step, okay? It adds up to the balanced chemical equation, and it reflects the rate law. I'm good, all right? Let's look again. All right, they've given you a reaction. They've said for this reaction, the experimental rate law is then they say write a proposed mechanism for this. Well, the proposed mechanism is going to reflect the balanced chemical equation. I mean, if the rate law reflects the balanced chemical equation, then it is fine. So we're going to do the same thing. Step 1, dot dot, OH plus CH3Br goes to CH3OH plus Br. And this is the slow step, because the slow step must reflect the rate law. All right, so if they ask you to come up with a mechanism, chances are it'll be one step, all right? And that's all you have to do. Sometimes it's so easy that they trip you up with that. Okay, so that is the rest of lesson 6 to the end of lesson 7. We'll do one more video on lesson 8 and have kinetics be done.